Okay, here we go, Abby. Question number 4 with the explanation. Here's our basic problem. This is a weak base, and it is being titrated with a strong acid. The equation I've put up there is an equation, it's like a generic equation showing a base in water. It yields its conjugate acid, that's the BH. Hold on, let me get my pen. I don't have a very good pen today. So here's your base, here's your conjugate acid, yielding hydroxide ions, so it is a base. So the pH at the start of the titration, at this point our volume is so not important. So again, I started off with the generic equation, and I could have put ammonia here and ammonium here, but it's the same thing. We don't care about the volume. I'm just interested in the concentration of the hydroxide ions. This is where we start initially. We have a 2 molar solution, and at the very beginning, the very instantaneous beginning, I don't have any of this or any of this. But I know as it shifts towards equilibrium, I'm going to lose some of this. And because everything is a one-to-one relationship, I'm going to gain this, and I'm going to gain this. Now, I can use molarity as moles because the volume is not important for this. I could use moles and then later convert it back to molarity, but it doesn't matter. So here we go. The base is going to lose some. The conjugate acid and the hydroxide will gain some. So now we're ready to find the pH. And as I've seen before, you do know that it's products over reactants. So that's where the x squared comes from, and then we solve for x. And truthfully, we know x is so small that you can pretty much ignore this in your calculations. Later, I can show you how to use your calculator if you don't want to ignore x. But then we end up with a value here of x equals. Now, that is the concentration of both this and this. Well, since we're not interested in the concentration of ammonium, we're interested in the hydroxide ion, which gives us our POH, and then subtracting that from 14, you have your pH. Okay, to calculate the pH, once we've added 40 milliliters of hydrochloric acid, the first thing we need to do is figure out the moles of every major species that we have. And if you recall, to figure out the moles, you simply take the molarity, which is moles per liter, and multiply it times the volume of that particular substance. So for the ammonia, we end up with 0.2, and these are all in moles. All of these values are in moles. Then this is your value for your hydronium ion. Now for the hydronium, I only multiplied it times 0.04 liters. From the previous problem, because this is a weak base, the major species before we added the acid was this one, and this one. So I simply took the concentration of both the ammonium and the hydroxide that I figured out from the previous problem and multiplied it times the volume for the base. So remember, this is at the very start of the titration. So looking at this, looking at the titration, which reactant is going to control the reaction? Is it going to be the base, or is it going to be the acid? Who's in charge? Looking at the major species, we now have the moles of everything. At this point, we would usually find a limiting reactant, but because it's one-to-one, we can figure out who the limiting reactant is just by visually inspecting everything. So initially, if you compare the moles of the ammonia and the moles of the acid, we can clearly see that the acid's going to lose because there's a lot more base. Each one of these is going to consume, well, this base, I should say, is going to consume all of the acid. And the products are going to gain that same moles because it's all one-to-one. So as we add this acid, we're going to lose some base. All of this will be consumed. And then each one of the products will gain that number of moles. So that's the change portion. And at the end, we can see that there will be excess hydroxide, not excess acid. So this means we're still in the base zone. Now we're ready to see what the pH might be. To start with, you have to find the molarity of each of the species. And to do that, remember, we had moles from the previous problem. At this point, you're going to divide it by the total volume, which was 0.14 liters. So those are the values we end up with. All right, this is where we are. Now we just need to use the Henderson-Hasselbalch equation to finish this up. Remember, this is a base, and for a base, it is the opposite of the acid. We're going to use the conjugate acid divided by the base. Remember, for Henderson-Hasselbalch, if we're going to use the base here, it's going to be the conjugate acid over the conjugate base. And that'll give us our pOH. And the reason it's pOH is because this value is your Kb value, which gives us a pOH of 4.3 and a pH of 9.7. Now we're finally ready to do the last part of this problem. At the equivalence point, the base will equal the conjugate acid. So that's what I have here. Oh, let me get my really bad pen going. So here's our base, here's our conjugate acid. Those will be equal. So if you look at the Henderson-Hasselbalch equation, the negative log of 1 over 1 is 1, and that's 0, and that drops out of the equation. So therefore, our pOH is going to equal our pKb, which means I simply put the pOH and the K value into the negative log. So that'll give us a pH of 4.47 and a pH of 9.3. And I will work on the next problem for you. I hope my explanations helped instead of just seeing it visually. Let me know.